Okay, welcome back. We are going to start a new topic. It's on thermodynamic property relation, and essentially what we are going to do is we are going to relate the changes in the partial derivative of various different properties. We will try to connect these properties together. So, let me just first start with the basic changes in the thermodynamic property, which is of interest to us, and we have already discussed earlier that in thermodynamics we are not essentially interested in absolute value of the properties. We are interested in the changes in the properties. So, we can start with the entropic relation, which we have written earlier for an ideal gas. Okay, so we have got this one relation which we derived earlier, and there is another relation based on Cv So, this was one equation, and this was another equation for obtaining the changes in the entropy for an ideal gas. Now, we can also derive another relation for finding out the changes in entropy for an ideal gas. Without deriving, I am going to write this expression. Okay. And this changes in the entropy relation can be derived based on the path which you undertake from P1 V1 T1 to P2 V2 T2. Okay. So, our interest is to obtain similar kind of changes for other properties such as changes in internal energies, enthalpies and so forth. Okay. Now, as we know that for a simple compressible system we need two intensive variable for the pure system. Okay. So, one can write entropy, for example, as a function of Tp or as a function of Tv or as a function of Pv. Now, based on this, the intensive variable, the changes in the entropy expression will be different. Okay. One can write the differential form of S in the following way. Okay. And similarly for the second expression, so these are the three expressions which we can clearly write in differential form based on the partial derivative. Okay. And the previous values of delta S, apparently one can show that this is clearly derivable from this differential form of S. Now, if you recall, this expression has been already developed or has been defined in terms of heat capacity. So, we know that Cp is nothing but T, and similarly for Cv. Now, these two partial derivatives can be clearly written in terms of Cp and Cv, which are experimentally calculatable, which essentially means that you can calculate Cp and Cv from experiment. Hence, these partial derivatives are measurable in these two particular partial derivatives. But what about these four derivatives which are still left? So, in order to develop these four remaining partial derivative, we will start with the first law of thermodynamics, and from there we will try to derive a certain expression which we are going to say thermodynamic potential, okay, which relates different intensive variables. Okay. So, let me just start in this exercise in order to understand how to connect these partial derivatives or evaluate these remaining partial derivatives. Okay. So, let me start with the first law. Okay. We can write this del q by in TdS form for reversible case, and this is PdV. Now, this tells you that this is u is u as a function of s and v. Similarly, you can also write h, which is h plus which is u plus PV, is can be written in terms of differential form. dH is TdS plus VdP, which tells you that h is a function of s and p. Okay. Now, what we are interested is first is that if you are doing an experiment and you would like to evaluate your changes in internal energy, it will be difficult to control directly the entropy, and thus it is relevant to change this variable to something which is measurable in the experiment, such as temperature, volume and pressure. And this is the reason that we would like to change this u to some function which we can measure. Now, what we can do to obtain f, that we can make use of something called Legendre transformation. Okay. So, without giving a formal proof, if you want to change this variable from s to t, this can be done by taking this function u minus the variable which you would like to change and take the derivative of u, partial derivative of u with respect to the variable which you would like to change at constant v. Now, this from this expression, if you take the partial derivative of del u with respect to s, this is nothing but t. Okay. So, Legendre transformation allows you to change this variable from s to t by using simple way of using this particular equation or expression. Okay. And this particular expression we will going to call as A. A is nothing but u minus Ts, and we are going to define this A as Helmholtz function. Okay. So, you can take a differential equation, you can write this expression in differential form. Which is nothing but P dV minus S dt. So, it tells you that A is nothing but a function of T and V. That is what we wanted to obtain. Similarly, we can change S H to another function which depends on T and P as a variable using the same Legendre transformation, that will be H minus S del H by del S at P, which is nothing but H minus Ts using this function. Okay. And this H minus Ts is defined as G, which is we are going to call Gibbs free energy. Okay. We can write the differential form of G as dG is dH minus TdS S dt, which is nothing but VdP minus ST. Okay. So, based on this, we have now 4 different differential form of kind of energies. Okay. We can summarize this. So, we from the first law we obtained TdS minus PdV. Okay. And the definition of enthalpy, from there we obtained dS plus VdP. Then we change this u from SV to TV and obtain this function called Helmholtz function, and we can write as dA in differential form. Similarly, we can write for dG. Okay. Now, this 4 set of equation is also called sometimes Gibbs equation. Okay. And this is nothing but, these 4 equations is nothing but differential form of 4 thermodynamic function U, H, A and G. U is internal energy, H is enthalpy, A is Helmholtz function, okay, or sometimes we call it Helmholtz free energy, or potential. Similarly, G is Gibbs free energy or potential. So, that is free energy or Gibbs free energy or Gibbs potential. The potential is basically related to the maximum work which we can obtain from a system, and this can be related to the minimum value of the free energy or the Helmholtz free energy or Gibbs free energy, depending on the intensive variable. Thus, it can be shown that the amount of maximum work is related to the free energies, and that is why they call it free energy or energy available for doing some work. Okay. Now, what our interest is to find out the remaining 4 partial derivative which we mentioned earlier here. Okay. So, we need to connect this partial derivative to something which we can measure. So, what we are going to do is, first we are going to define something called exactness of the differential equation, and this is something which we are going to use this 4 equation later to connect this partial derivative which we would like to find the relations with something measurable. So, let us first define differential equation, okay, where m is and n is your del z by del x. Okay. Now, we can take a partial derivative of m with respect to y, keeping x constant. This is going to be del square z del x del y. This you can rearrange, del y del x, okay, and this should be equal to del n by del x y. Okay. Now, this becomes the statement of exactness of z, differential form of z. So, that means if dz is exact, that means exact differential, then this condition must hold. That means this dz is exact. Okay. Now, making use of this expression, we can use this equality which will connect the partial derivative of your m with respect to y, and that to the your partial derivative with n with respect to your x. And this is something which we can now use these 4 equations to come up with this set of relations based on this exactness expression. Okay. In order to make use of this exactness expression for on these 4 equations, I will try to reproduce first this equation, thermodynamic potential equations. Okay, so here we have just swapped it so that we can have in one column S of t. So, now making use of exactness expression, here we can get del t by del v as minus of del p by del s. The next expression is del t by del p s is del v by del s p. So, this becomes this. The fourth expression is del p by del Cv. Okay, so this becomes from here, and the last we have del s by del p at constant t equal to minus del v by del t at constant p. Okay. Now, this 4 equation or expression which we got, or relation which we got, is also called Maxwell relation. Okay. Now, sometimes it becomes very difficult to remember this. So, there are many ways which people have come in order to keep it in the memory. So, one way is, of course, you can write this 4 thermodynamic potential relations and directly use the exactness expression in order to get this 4 relation. Other ways also you can come up with this mnemonic diagram. Okay, so instead of using specific properties, specific energies or free energies, potential, we'll use here capital. Okay, so what I'm doing here is I am writing this alphabetically: A, G, then H is H as a function of S and P, U is a function of S and V. Okay, and then I can draw a square. Okay, starting with A followed by G, H, U. Now A is connected to TV and G is connected to TP. So T is common vertex. So T is here, V is here. Now here is T, and of course G is, the independent variables are T and here has to be P. H is P and this has to be S, and of course U is V and S. So the key was to make sure that we have a connected corner between A and G. AGUH was used. So the other thing which we do is that when we make this square, we make not just square but also this kind of diagonal where we put the arrow towards the upper edge, and then we may make use of this alphabetical order of AGHU. Okay, so then you can come up with this way of getting, let's say, du. So du is the sign, okay, and then the coefficient, and the independent variables are V and S. So we'll start with, let's say, ds plus sign, coefficient, and dv. Okay, so what is the sign? For example, sign in this case is given by this arrow. If it is pointing away from S, okay, then it's going to be positive, and the coefficient is where it intersect, that is ut. So this becomes positive t ds plus this sign, which we are going to take it V, which is towards itself, so that is going to be a negative, and the coefficient is of course P, diagonally opposite to V. Okay, so the variables are at the end of the line here, and the coefficient is the diagonally opposite variable or vertex. Sign is when the arrow is away from the independent variable, which is positive. If it is towards itself, then it's negative. So that is how we can also make use of this kind of diagram. Okay, so with this we can also do some exercise here. So D, let's say G. Okay, again we can think of sign, coefficient, let's say this is your T, plus sign, coefficient, your dp. Sign for the case of T is going to be negative because it's towards itself. Coefficient is S, and the sign is positive, and coefficient is V. Okay, so that's how you will get minus S dt plus V dp. Okay, so this is one way of getting this four Maxwell relation which connects different variables. Now you can clearly remember the thermodynamic relations directly by understanding the way it was derived, or you can make use of this kind of diagram in order to remember that. Okay, so we are going to make use of this Maxwell relations in order to come up with the different variables or changes in the variable which cannot be measured directly from experiment. Hence we may need to use such a relation in order to convert to some variables which can be measured experimentally. Okay, before I end this lecture, let me also write down these two expressions which we are going to also commonly use. So one is called reciprocative relation. Okay, so this is an okay, so this is something which is well known. and the other one is a cyclic relation. Okay, cyclic relation where we use 3 variables. Okay, so remember here this is kept constant, so you're just changing the swapping the variables. So this del y by del z, keeping x constant, and del z by del x y, this is minus 1. Okay, so this is the cyclic relation. So we are going to make use of cyclic relation, reciprocity relation, and as well as the Maxwell relation in order to come up with the various relation between the variables which are of interest to us. Okay, so with this I will end this lecture. In the next lecture we will try to make use of this relation to solve some to come up with this interesting aspect of thermodynamics. Okay, so see you in the next lecture.